climate, in my view, is breaking down. I prefer, when I'm teaching about climate change, not to call it climate change. I was telling Peter beforehand, calling it climate change is like saying that, you know, an invading army is unwelcome guests. You know, we are facing a crisis. We're going to be focusing today mostly on issues around engineering, creative engineering responses. And I don't know whether it's at planetary scale or regional scale. We can learn all about that. But I just want to also flag up that we're also going through the 6th Great Mass Extinction event. You know, we are now, and it's anthropogenic, it's human caused land use changes, particularly our love affair, particularly with red meat. So just get a plug in there in terms of our unsustainable food-based system, but also our increasingly unsustainable forms of urbanisation and land use planning. That we have these twin crises of the climate and the ecological or biodiversity challenges. And for me, and I come from, in terms of the disciplinary backgrounds, I'm a heterodox political economist. I believe that most modern economics that is taught in universities and secondary schools, and indeed informs government policy, is ecologically and biophysically ignorant. And that's part of the problem that we have. We have an ecocidal economic model, which, if you were a scientist, you would not design an economy the way ours is, in terms of a linear take, make and throw away based upon endless growth. And I do really welcome, Dr. Ye Tao from the Roland Institute at Harvard, because we were just talking beforehand about the importance that if it is a crisis, we need to name it as such, and therefore move beyond even academic business as usual. And what I mean by that, and a lot of lip service is given by universities and funding bodies to interdisciplinarity. You probably heard that term. Well, to me, this is a crisis. We're going to have to get all the disciplines together to figure out what the solutions are. And we'll disagree, and that's absolutely healthy and fine. But I think it's time to move beyond either rhetorics around the need for interdisciplinarity and to really start seed funding, supporting. This is a modest attempt today. And it might be something that we can come back at the end if people enjoy this interaction between a heterodox political economist, and I don't know what your disciplinary background, it's certainly not social science, it's much more sensible, engineering, physics, and maybe knowing something with the second law and third law of thermodynamics, which always escapes me. But I do think that there is a challenge for us in terms of reaching out beyond our disciplinary silos. And the last thing I'd say before I hand over to Dr. Yao Dr. Tao, is that there is also a lot of rhetoric in politics. How many of you, put your hands up if you are from Northern Ireland, did you know that the Northern Ireland Assembly declared a climate and ecological emergency in February last year? If you live in Belfast, did you know that Belfast City Council in October 2019 declared a climate and ecological emergency? So we have these declarations, and then what happens? It may be a separate event that we could consider having, is that, in my mind, the pandemic is what a real emergency looks like. The rapid changes by the state, furloughing workers, washing our hands, wearing masks, social distancing, all the arsake that went along with the things that we had to do. And there was, at least unevenly, well, certainly this side of the water, I have to say it was less so maybe in Trump's America, there was governments being led by the science. So if governments are being, as I say, unevenly led by the science in dealing with the pandemic, why is it that when we've had at least 30 or 40 years of ever-increasing climate evidence of our climate breaking down, why don't we see the same action? And that's an issue of politics, an issue of the way in which the Koch brothers in America, or Rupert Murdoch here in the UK, how the media often has manipulated this debate. There are vested interests that are challenged by any move away from a carbon-based, growth-orientated economic system. But that's enough about me. So I've laid out some of the problems and some of the context of why we're here, and I do encourage you, particularly those of you who are based in Belfast or at Queen's, it's something we don't do enough. We should be inviting the community into Queen's and encouraging students, PhD students, to propose seminars and so on, rather than being passive, because again, it's an emergency. We need to have more of these debates and discussions. So, as I say, you're all very welcome. And I'm going to hand over now to Dr. Tao, whose title for the talk has changed a little bit in a number of iterations. I'm going to read out the one here. Mirrors for Earth's Energy Rebalancing. That's the MEER, I take it, the acronym. And then this one I love, Flattening Diamond and the Climate Monster. So you're very welcome. I look forward to hearing from you.
All right. Thanks for the very good introduction that paves the ground for what I'm about to share. And it's also for me the first time presenting in public outside of my institute since about 2 years. And I think it's a very nice crowd, but apparently it's already quite multidisciplinary. So I'm looking forward to a discussion afterwards, and hopefully I'll live up to some of the standards set forth by the introduction. So how many of you are in engineering? So there's one. The other are in maybe natural science, social science, I suppose. So I wasn't sure what to expect, so I used this cover slide, and that's a picture of a single crystal diamond, which started off pretty rough on the surface. And then in my group, we have a project on how to make it super flat. So this region over there is close to atomic flatness, and we use a very simple method. And you'll probably, I can discuss how my training in nanoscience actually has conceptually inspired a solution for the climate change. It has to do with dimensionality. So hopefully that becomes clear later on. So the project was conceived at the Roland Institute, which is like a very small building. We have about 40 staff members working in about 10 different research groups. And each group is headed by a Roland Fellow, or essentially fresh PhD graduates who are given the opportunity to head an entire lab and have 5 years of funding to do whatever research you fancy. And we're also allowed to change course halfway if we think there's an emergency, such as the case in my case. I flipped, turned 180 degrees. So in the talk you will see that I like to make a lot of two-dimensional plots to make things conceptually clear. And here is one rendition plotting different engineering disciplines happening at the Roland on an axis which denotes the size of the object you're trying to study, and the other is how complex the interactions are in your system of interest. So as you can see, we cover basically all the hot areas of science and engineering, despite our small size. And in my group, we are a goal-driven engineering science group, and so the target is to build a scanning force microscope that can deliver atomic resolution images of very tiny objects via a combination of MRI principles and atomic force microscope principles. In order to build such a microscope, we often find you have to do so much engineering that's not directly related to the particular instrument. So examples include we are learning to carve these three-dimensional single crystal objects from a silicon wafer, and the dimension of this is roughly 100, 200 nanometers wide for each of the stem, which is like 1,000 atoms. So these are very tiny objects. And here is another example where we learned to machine a surface with atomic depth resolution. So imagine when you make any object, you have to use machines to turn a piece of bulk metal into your components, and we are learning to do that with atomic resolution. So these are some of the work that carried out in my group on the route to a very lofty target. So won't go into the details, but even to make one of these, we need to build multiple instruments dedicated to certain steps in the fabrication. Same thing goes for this machining project, which was done in an ancient scanning electron microscope that we tore down and rebuilt from scratch. But of course, all that is fun, and we can spend one's lifetime in those silos, but it's a little bit slow. But the point is, I think it's quite effective for expanding our horizons and the technical capabilities to focus on some very lofty targets, and that you're compelled to invent new engineering in process discovering new science, and the new results will oftentimes enable solving other problems that you didn't initially think about. But of course, there is an emergency going on, and the world is literally on fire, so it didn't really make sense to be stuck in our silos and just be, let's say, myopic. for the next decade. That would be quite weird. So after I started to look into the issue, in sometimes around 2017, became quite clear that the reason why society has been incapable of addressing these problems is because there's a bunch of common sense that we hold as self-evident. Even for people who consider themselves literate and liberal, I think many of these we will try to examine them in detail today. So one common belief is that 100% renewable will solve the climate change crisis. Another is that planting 1 billion, and some people were proposing 1 trillion trees would help curb the effect of climate change. And now there is all the major companies and CEOs of corporations that's controlling this civilization have these CO2 capturing prizes, Earth X, etc., and the Elon Musk's prize, and also the one hosted by the UK royal family. Yeah. So those are all focusing on, for example, CO2 capture as a mean way forward. And today we'll examine these common sense in some technical detail. Hopefully, you will really appreciate from the fundamental principles why these may not be as straightforward as they are claimed to be. But of course, underneath all of these, the real causal problem for all of this is the combination of capitalism with the procedural democracy. And that's obviously not my area of expertise, but in looking into the issue of climate change from a scientific point of view deeply, then you inevitably eventually end up looking at these issues. I will leave the discussion to experts, including John here, and rather focus attention on just the technical aspects today. So here is a very simple model that would enable anybody, even like elementary school students, to understand the fundamental mechanism of climate breakdown. So we can conceive of the universe as a collection of what we call nodes, of forms of matter that's in constant flux. And the two nodes that we need to be concerned with in understanding climate change, one is the collection of greenhouse gases in the atmosphere. That doesn't include, for example, carbon that's buried, that's in another location. So it has to be a form of matter in a particular location. That's a node. The other is not matter, it's heat, a form of energy, but you can conceive of energy as a form of entity as well. So the other node is the amount of heat trapped in the Earth's biosphere. So when all the source rate and sink rates are balanced, the system will progress in time without any apparent change in the actual size, and that's what we call stability, or in a sense, sustainability. True sustainability is the gazillion nodes in your whole system have their source and sink rate always balanced. And in theory, that system cannot change, and that's the definition of sustainability, which unfortunately the field has never really defined. So what happened on Earth recently was we cranked up the source rate for the greenhouse gas node. And when you have an imbalance of what's coming in and versus what's going out, there will be a temporal change in the size of this node, and in this case, an increase over time. We don't need to be worried about the specific coupling between the gases and the heat, but suffice it to say that in pictorial terms, it's basically like a spring valve. So when it's bigger, it's weighing heavily on this valve and shutting down partially, leading once again to an imbalance of heat coming in and heat going out. And then as a consequence, we have increasing size of the heat node. And here is a plot of actual data of the atmospheric CO2 concentration on the x-axis and the average land temperature on the y-axis over the past roughly 1 million years. And I've color-coded the data points in logarithmic color code, so that the red through yellow happened very recently, through less than 0.1% of the entire temperature range. So before we started to burn coal at around this point, Earth was displaying some like natural variability on a 10,000 or 100,000 a year time scale. That's like the glacial and interglacial oscillations. And over time scale of 1,000 years previously, Earth can only wander around in this plane by a very tiny bit, denoted by these ranges. But since we start to burn coal, we obviously have driven the system out of its natural habitat, let's say. So this visualization is a irrefutable evidence for human perturbation to the climate and Earth system. So some people might welcome warming climate as people here. You know, it's nicer to have enjoyed this weather in November, October. But is that really good for our climate and ecosystems? This paper came out quite recently, and looking at the change in bumblebee populations over Europe and North America, and comparing that against temperature fluctuation or changes over the same time frame. We see that there is a very strong correlation of laws with heating, and the authors actually also analyzed other contributing variables, including land use, etc. But they concluded that land use does not really explain the trends, and it's really the temperature change, which might be the most likely causal contributor. I think evidence for that conclusion is made clear if we look at regions where there's been an increase in population, like the blue areas, and those corresponds to regions that have undergone cooling. So presumably land change would have not discriminated against cooling and warming regions. So that's directly visual evidence for the lack of impact of land use as far as this particular species is concerned. So that's, I think, in my reading, I haven't really followed up with this field. One of the first mechanistic studies on the case of insects. Of course, there's like two prior reports of exponential decay of insect biomass in Germany and also in Central America. And if you fit the data to exponential decay, one finds decay time constant of 12 years. So that's a lifetime of tritium, radioactive isotope. So when insects, which are stable for millions of years, are suddenly disappearing like tritium, something must be going horribly wrong. So what might be causing this sort of biodiversity loss? Well, we animals, we need a certain amount of energy just to stay alive if we're exposed to increasing temperatures, because metabolic processes get faster and we need to repair more cellular damage when there's a heat stress. So that's denoted by this black curve. And the body also has a upper bound capacity at a rate at which it can utilize oxygen to produce useful nutrients and ATP in order to perform work. So the difference between what you can metabolize or produce, the rate of energy that you can produce at maximum, and what you need to sustain this basal metabolic function is denoted in green, and that's the extra energy you have to do useful work from a biosystem perspective, like growth, cellular maintenance, and the reproduction. So the same sort of bell curve can be observed for plants as well, and for different plant processes, they have different temperature dependence. But of course, they are usually limited by the curve which drops first, and in this case, oftentimes it's photosynthesis. Above about like 25, 30 degrees, we have to, plants become less efficient when they're exposed to very warm weather and strong light. The same sort of curve can even be observed for other simpler organisms, but the mechanism here is protein denaturing. But regardless, most forms of life that we have studied will perform very poorly and doing so very quickly once temperature rises a little bit beyond their optimum temperature. So there is a long-term study over the past 20 years looking at the result of gentle heating, average rising local temperature by an average of like 2 to 3 degrees Celsius, and the impact of that on this particular species of small mountain flowers. And the researcher found that the plant essentially lost their fertility under only 2 to 3 degrees of perturbation. And the longevity of plants also dropped by a factor roughly 2. So the combined result of losing fertility and experiencing premature death has led the study area, to lose all of its local species of this type. So that's one example of the exquisite sensitivity of biological systems to even very gentle heating. And as far as human system is concerned, I think the limiting factor is, of course, agriculture, because that's where we derive our energy from as a human animal. And because of the sensitivity of crops to this temperature in photosynthesis, there's a very sharp drop of productivity beyond about 28 to 30 degree temperature range. And over the past half a century, we have experienced up to like 30% drop in total factor productivity. And the trend is really not going well. And the slope of this will become progressively even sharper because of the underlying biological dependence. So basically, there's a shift in mean temperature, which we discussed, but what's really scary is the change in the probability for extreme events when you have a shifting mean. But the data actually tells that the story is actually worse, because instead of just shifting parallel, we also see a widening of the distribution. So the extremes are happening faster than due to a simple shift of the mean for a normal distribution. So summarizing, essentially on the order of 1,000 papers that I and my teams have examined, it's quite clear that the current trajectory is bringing us very quickly outside of a phase space of habitability in the language of material scientists. And we essentially have already crossed an average temperature or climate that's conducive to a healthy ecosystem on Earth. And because there is a time lag from the perturbation to the response, even if we were to hold current temperature stable, we can expect to see continued degradation of ecosystem. And if somehow we managed, and essentially without intervention, we're guaranteed to cross the 2 degrees Celsius, then there is little hope for the system to recover from a biological point of view. But there's detail that you might have noticed. There is a bunch of thermal boundaries that will be really bad for ecosystem, but there's also boundaries along the CO2 axis. The upper one being a concentration of CO2 where it starts to become toxic to animals from acidity point of view, acidification of the oceans and also of your blood. But we will not really approach that boundary in the near future. And if we plot that on a time axis, we are already on a collision course with the thermal boundary, but fossil fuels that we have established, the reserve that we have established, won't be sufficient to really induce the toxicity effect. So maybe that's reason to really focus on the temperature node rather than the material CO2 greenhouse gas node in the atmosphere. So that's a tantalizing possibility. And these analyses, we first share them only at conferences like back in 2019, but since then, the projections using very just linear projection has been pretty much on track with the most sophisticated climate and biological models. So, which predict that within the next decades, and starting from now, large areas of the oceans and land will undergo ecological degradation on a massive scale. So what needs to happen is quite clear. But we need to somehow steer the Earth system in a direction pointing towards negative temperature. And it doesn't really matter if we choose to do that by decreasing CO2 at the same time. We're actually allowing some CO2 emission, but what's really critical is to go down along the temperature axis. And it's actually possible to permit much higher emissions as long as we go down. So this trajectory will be, from an ecosystem perspective, will be very similar to the effect of this one. And going from the right side is actually preferable to going from the left side. due to an effect we will discuss later. Okay, now let's look at the solutions that's been discussed in the mainstream media. So remember that we have these two nodes as what defines the problem. We have 4 different rates. The source and sink rate for the heat are what we call direct knobs, because they directly address and control the amount of heat that's in the atmosphere. And the comparable rates for the greenhouse gases are indirect, because they indirectly impact the node. That's really important. So examples of strategies targeting source rate for greenhouse gases include green renewable energy, because then we would be able to reduce this error. And the same for carbon capture sequestration at sites. That's also to reduce the rate at which we implement or emit greenhouse gases. If you want to capture what's already being emitted, you are trying to increase the sink rate, and methods include nature-based solutions and industrial direct air capture. Geoengineering methods include stratospheric aerosol injection, marine cloud brightening, and many others are trying to directly affect the rate of heat input into the biosphere. And the MEER reflection framework that we're developing actually synergistically tries to tackle several of these knobs together, but with a triage-like process of prioritizing some over others, dictated by constraints in time, material, and energy. And the first one we'll be focusing on is shutting down the rate of input. It's also possible to actually open up another channel for ejecting heat into space, but we will not talk about that today. So I think it's useful to appreciate what we are fighting against, essentially the size of the climate atmosphere. And we can, similarly to the simple model, take the material and the energy perspectives. The total amount of, again, CO2 equivalent that's in excess in the environment is 3 teratons. So tera is 10 to the 12th. So that's roughly 10,000 times human biomass. From energy perspective, the difference between how quickly heat is coming in minus the heat is going out, the difference is what's driving the current warming. That power is between 400 and 1,000 terawatts. So the 1,000 comes about because half of the heating is currently hidden by clouds and aerosols. When you have a bonfire, you actually induce more clouds and cover, and that counterintuitively, in the short term, helps cooling in the local region. So the difference stems from that.
They're the local lads.
Don't tell them that.
Harvard supports born on bonfires.
We should have a department like what material to burn to bring about the best. So in comparison, last year we used, in human civilization, we currently dissipate 18 terawatts. So that's the fossil fuel power that we have, which is essentially very much dwarfed by the problem that's out there. So that just shows how powerless we are from an energy perspective. Okay. All right, so here is the same information, but depicted as the shape or size of a rectangle. So that's your part of the problem, how much weight in CO2 that each of you, your mass is like that. You have to sequester in order, within the next 10 years, by the way, in order to make a difference. And of course, I'm depicting everything piled up together so it looks more manageable. But in reality, this mass is distributed, over the entire atmosphere and oceans. So I put 1 pixel up there, and that pixel is roughly 100 times more concentrated than the actual situation out there. So imagine yourself, and you're roaming around this atmosphere arena and trying to sweep up those little particles. You need to sweep 1,000 times the area represented by the whole frame every single day for the rest of your life, over 40 years, to sweep up this amount of CO2. So that's the task ahead of you. In terms of energy, when you burn coal or biomass, that's how much heat you can produce. But the heat that each of you has to somehow eject into the universe and into space is this much, or the power. Right? So this is happening continuously, so it's a watt per time. But I guess that looks a bit more manageable than this one. Okay, now let's put some criteria on what makes any solution feasible. It's quite stringent, right? When you are actually doing something, you have to say yes to a whole range of criteria that includes whether it works even in principle, right? It has to be physical. The solution has to be physical and consistent with what's required. We need to have enough materials to build infrastructure to implement your solution, and also enough energy to both build and to run the process that's required. And it has to be fast enough. So any feasible solution needs to satisfy at least these 4 requirements. And with those metrics in hand, let's examine the mainstream proposals. So reforestation and afforestation, basically letting forests grow back in crop fields and imposing new monocultures onto biomes that initially didn't support forests, are touted as a solution for climate change. So let's examine this from the perspective of scalability. This box represents how much greenhouse gas you need to capture back in order to stay within the safe limit. So the total global afforestation potential has the size of this little box, and even a smaller one for reforestation. And those boxes will fill very, very, very slowly over the time scale of a century to 2 centuries. So if we're lucky and somehow we already achieved carbon neutrality in the year 2100, and somewhere between that, we would be left with a problem which looks pretty much the same as what we started with. And that requires so that's just looking at the scalability, but in practice, it's essentially impossible, regardless of how much effort we put into to even fill a fraction of those things. What about capturing them by industrial methods? So the problem here is that there is one energy that we essentially wasted in the act of emitting pure CO2 from exhaust gases into the atmosphere. So when you allow a concentrated gas to emit and mix and be diluted, you lose what's called a free energy of mixing. In order to reverse the process, we need to invest at least what you have lost theoretically, but oftentimes there's no perfect, it's not reversible. So we currently need to invest roughly 20 times the amount of energy in order to reverse the process. So we're looking at investing 6,000 exajoules just to overcome this energy of mixing. And the requirement is it takes a lot of effort to separate salt and pepper once you have mixed it. And the US military spends only 1 exajoule per year, and is one of the largest polluters in the world. So if somehow magically we could come up with an effort that rivals the US military in size, we're looking at 6,000 years of energy expenditure in order to perform this task. What about the material side? So we have analyzed the energy. So to capture CO2 by industrial means, we need a bunch of basic compounds, because CO2 is slightly acidic, so a base and acid like to react, and that's how you can fix them and sift them out of the air. So either sodium hydroxide or ammonia. If we want to build infrastructure that can capture our current emissions, we need to ramp up the production of these chemicals each by more than 2 orders of magnitude. And the energy required to make them combined would be larger than what we had available as fossil fuel energy. So basically we cannot make enough material to capture back what we have emitted. And to run the process, again, also costs additional energy. So the conclusion is that by these analyses, we need 13 years of global energy to just capture back 1 year of emissions. You can use more efficient energy to do the process like heat pumps, but even so, many parts of the world would not even break even in the process. So energy-wise, it looks pretty hopeless. And of course, you need actual material and infrastructure. So to capture back 1% of current emissions, many important materials such as concrete needs to be ramped up by 5%, so you're creating more problem than you're solving. And in terms of impact to ecosystem, it's also on average on the order of 1%, so we pretty much trash the entire ecosystem if we want to just capture back contemporary emissions. What about renewable energy? So burning fossil fuel obviously drives up emissions embodied in CO2 and methane and nitrous oxide. But there's also emission of the mist from the bonfires, which is denoted by these red and orange bands. And in the atmosphere, they have the opposite effect. They have a cooling effect. The thing is, after July 11th, maybe by July 18th, air has cleared up again, right? So these things, as soon as we stop burning, they drop down to zero. And the impact on ecosystem or climate system is that we would add this much of warming on top of what we have from greenhouse gases. And this fact is not being discussed widely because the scientists who understand the data and people who are spokespeople for the climate worry that the population is still, or this information could be hijacked by fossil fuel companies to prolong their business model. So let's understand the impact of adding this much additional heating essentially instantaneously to the climate system. So the driving is like having a step function added to the energy imbalance. And the response of the Earth system to this sort of step function is what we call the step response of the climate. And we know that pretty well from models and also observation that roughly 50% of heating would be realized within 10 years of such a step function drive. And the remaining 50% of the heating, the locked-in warming, which we haven't really experienced currently, would take a much longer time scale to realize, but it's still there. So the magnitude of how much heating that is then hidden has been assessed to be about 1.2 watt per meter squared. That's like a LED light everywhere on Earth. So that's how much, unfortunately, fossil fuel economy is cooling the Earth temporarily. And the impact of this one on equilibrium temperature on Earth can be calculated by multiplying the slope that correlates the heating to temperature change with the actual power density. So it's very conveniently roughly 1 degree of heating that's hidden. So in summary, while renewable energies allow us to walk slower along the CO2 axis, it doesn't do anything to induce a negative mobility on the temperature axis. So it's not really a solution. It's something necessary that we have to do, but it's not a solution to the climate crisis. So in summary, renewable energies are not solutions because they don't work in principle for addressing the ecological crisis that's out there. And many solutions, including natural and technical drawdown, cannot be scaled. We don't have the energy or the time to implement them. So the unfortunate conclusion from this analysis is that there is no concept in mainstream discussions that could even in principle halt the climate catastrophe. So coming back to COP26, even if the most fantastic results were achieved and everything climate activists and renewable energy people call for have been agreed on and implemented with an iron fist, this civilization is still finished because existing solutions do not work in principle, or they simply are not compatible with engineering constraints. So, whereas 5 years ago I was extremely interested in making this fantastic 3D microscope, I think it's time to really understand the urgency and reprioritize. And that's why I'm here, because education and also encouraging the next generation of engineers and social scientists is very important for this process. So since about 2018, we actually got our hands dirty. We started to build new instrumentation that's trying to address the climate problem, including coupling MEERs, which we'll discuss as a very potent tool for cooling with renewable energy capture. We will, in the coming year and two, study the compatibility of cooling MEERs with agriculture and ecosystem recovery, and how they interact with natural system, including birds and the small mammals and humans. And also the possibility for deploying MEERs in different environments, including oceans and Arctic, and their impact on temperature and ecosystems, and also learning to work with nature in order to embed ourselves into natural cycles in the process of achieving true sustainability defined by closure of all biogeochemical loops. So to start with, let's look at CO2. And rather than considering it as just bad and evil, let's consider its different physiological impact. So obviously, it's trapping heat. And we understand very well it's a very urgent problem. What's not really talked about is that CO2 also allows all plants to grow faster and use less water in the process. So when the CO2 is in the air at higher concentration, then the rate of diffusion from the air into the leaves becomes faster, driven by concentration gradient. And when that's the case, leaves can afford to close their stomata, which are pores where CO2 can diffuse in, but which also allow water to escape. And that's why plants need water, because the stomata pores on the leaves are continuously emitting water while letting in CO2. So when the concentration gradient is higher, they can close it, get the same flux of CO2 in, and at the same time reduce the flux of water out. So they become more efficient at using water and more drought tolerant. So if somehow we can have a factor X that, with a laser sharp focus, address the heat while preserving the other problem, and also eventually be compatible with addressing this longer term problem, then we turn CO2 from a pure villain into our ally in this ecological remediation process. So, as you already read in the title, that X are MEERs. So let's first assess feasibility. The question is, how big of a MEER do we need in order to cancel the heating effect, that's a red block, for 1 ton of CO2? The amount of CO2 that's in excess in the atmosphere causing the heat is 140 ppm in excess compared to the 280 pre-industrial. And that's roughly 1 teraton. We know how much they're warming. So the warming impact per ton can be very easily calculated by division. We also assessed the local radiated forcing for a 1 meter squared of MEER, which we'll discuss later. It's roughly 100 watts of cooling per meter squared. And we know the surface area of the Earth. So the impact of a single 1 meter squared MEER, when averaged over the Earth, comes to very close to the same order of magnitude as the heating impact per ton of CO2. So then you take the ratio of the warming divided by heating, then you get a ratio of 1 ton per 10 meters squared of MEER. Is that clear? Yeah. So how much does it take in terms of dollar amount, to make such a device? The energy required to make the glass is only $1 based on historical price of fossil fuel. And that's how MEERs and glass are made, driven by fossil fuel. And you can buy the same area of glass for about $10 at market price. So the cost, if it's done, globally and in a coordinate fashion, should sit somewhere between $1 to $10 per ton of CO2 canceled. And that's right now 1 to 2 orders of magnitude cheaper than what other proposals can accomplish. So soda lime glass is everywhere. They're 100% recyclable. So if you make glass mirrors using this material, you can reuse it just melting it down. The little bit of coating, optical coating, is utterly negligible. So it will become transparent glass again once you just melt it. And it's mechanically stable, and they're corrosion resistant. So glass can last for decades to centuries if you don't actively break them. And soda lime glass in particular are composed of elements, which luckily for us happen to be the most abundant elements in Earth's crust. So they're so abundant that just using established reserves for these minerals, we can make enough glass to cancel the heating of 1,100 ppm of CO2 equivalent. And that's way beyond what we can achieve by burning up all the fossil fuel reserve in the ground. Which basically means, in principle, even if we were just to do this project brute force, by building MEERs to cancel CO2, it's still a feasible project in contrast to everything else that we have discussed. But of course, we want to avoid having to do that. So how do we leverage the other powers of MEER in order to stop the fossil fuel industry and really transition into a sustainable civilization? So we already mentioned that it's important to do the ramping down slowly because of the hidden warming that's in the atmosphere due to the aerosols. If you have a MEERs that's doing the cooling, then we can then safely ramp down greenhouse gas emissions and the aerosol emissions that's co-emitted. And that this effect exists has been observed in the early days of COVID. So this dotted curve represents the number of flights in Europe after the lockdown. And with the decrease in flight and also other economic activities, the sky really cleared up. Specifically, the yellow bars denote direct irradiance, basically sunlight that's coming down without being scattered by clouds, etc. So not only you have clear skies, but also the total amount of energy reaching Earth reached an absolute record as a result of cleaning up the air. And the consequence for that would be heating of the ground. So MEERs are used in a range of very efficient renewable energies that's known as the concentrated solar energies in different implementation. So cheaper MEERs used for cooling would enable these to be more competitive, which would then hasten the speed of ramping down fossil fuels. And better climate, cooler climate would also make agriculture more productive, as we reviewed at the beginning of the talk. And ecosystems, because they're also plant-based, would also grow faster, and which in turn would finally enable natural solutions like reforestation and hopefully not afforestation, just reforestation to play their part in helping to draw down greenhouse gases. So that's how we envision the central element X to enable a holistic and a stepwise journey towards a sustainable and livable planet. All right, so let's talk about some actual simulations and data. As you can see in this picture, we see different reflections on the two different MEERs. And that's an illustration of the fact that light comes in to the ground at different angles once it's reaching Earth due to a range of processes scattering and also scattering off of cloud. So at any location, you can describe the light field by the two parameters denoted by the angle of phi, the azimuthal, and the polar angle, theta. So here is a color map showing the intensity of light reaching ground in one of our experimental sites in July. So that's the phi angle, basically the 180 degrees around you, and this axis denotes the theta angle. Most of the light coming down are pointing down, so we're not really keeping track of the light scattered up, so that's why it's basically zero up above horizon. So here we read about 1,000 watts per meter squared coming down. That's the dominant angle. After this light has been reflected by MEER by specular reflection, it travels back the different layers of atmosphere. And then upon exit, it will show a very similar distribution. And the intensity would have been decreased by roughly 20%. So we are able to reflect what's coming down to the ground back with the efficiency of 70 to 80%. So it's feasible, essentially, from a theoretical point of view. One can also do a similar assessment of such efficiency based on more top-down satellite-based data analysis. And here, we're plotting how efficient MEERs are at different locations of the Earth when they are all pretty much adjusted to their optimal angles. And many areas are compatible with above 100 watts per meter squared of local cooling, and that's the number we used in the assessment of feasibility and cost. All right, now let's look again how MEERs allow us to amplify your very limited thermal power to overwhelm the problem that we're trying to tackle. So now let's assume you used all of your energy exclusively to make MEER, just for illustration purposes. So that you made this MEER. Over time of 1 month, if you set this thing in the field outside, you would have effectively ejected this much power from Earth. And the size of the effective power actually grows linearly with the time of deployment. Because when it's outside there, it's passive. You're not giving no more energy input, but it's continuously ejecting away thermal power. So your efficiency grows with time of installation and the durability. So already by 1 year, each person in principle would have been able to completely cancel your part of the problem. Another analogy. So when we are trying to cool your room, you have to input some electricity through your AC. And your AC will take that amount of electricity or energy Q and move 3 times that from inside to the outside. So that's why heat pumps can be more efficient, because it's a heat transfer rather than heat generation process. The same calculation applied to MEER shows that instead of a fixed ratio of 3, the coefficient of performance actually becomes a function of time. Because again, once they're made, they're passive and they continue to give benefit without additional energy input. So the actual coefficient of performance for MEER is 100 times T, where T is the years in service. And typically, well-designed solar MEERs can last 50 years, essentially no problem. Which means even 30 years, we're looking at a coefficient performance of 3,000. So this amplification and durability is the fundamental reason from engineering perspective why we are able to tackle an energy problem that's much bigger than what we have in terms of starting energy. Of course, we are doing this cooling your house, you are actually damaging the planet indirectly through CO2 emissions. And again, conceptually, why the MEERs can function is because if you are trying to tackle the material box, the gas that's in the atmosphere, it's a 3D problem, you have to filter that. And that takes time and energy. And that's simply not feasible. But if you reduce the problem to the conversion step of light to heat, then it's a 2-dimensional engineering problem, and that becomes feasible. So let's talk about some actual data. So the experiment was implemented in New Hampshire, not the most drought-stricken area, but it still shows some effect. So these are the students, undergrads, who worked on that, and that's the collection of faculty that we're working with. And I got to know them through the Open Education Network. Brian Alexander, I don't know if you are aware of him. He talks about education reforms, and so I suggest you're looking up his videos, very relevant. And I saw a talk by Robin DeRosa, director of CoLab at Plymouth State, with Brian, and I called them up, and that's how we got to know this group of enthusiasts. So here are some pictures of our only 2 test devices in the very initial preliminary experiment. And here is the cooling power density for one of the devices using data measure the solar irradiance over the month of July this current year. We see that MEERs do not just cool their immediate ground underneath, but can cool a region. And that the size of this region is a function of how you install the MEER and how high off the ground you put it. In this particular case, it's for an installation height, which is 50 centimeters above ground, so they are very low. It's possible to increase, the area affected by raising them up in more or less a linear fashion. So, but nevertheless, for this very initial experiment, there is cooling that's observed in an area that's 6 to 8 times larger than the actual area. So these are measurements of soil temperature over the month of July at a point below the MEERs versus a neighboring point, which is still somewhat affected by the MEER, but it's far away to be mostly representative of background soil temperature fluctuations. And you can see very dramatic difference at midday, roughly around midday, the soil temperature up. And if we plot the difference, then some days it reaches a whopping 5 degrees Celsius of cooling. So for those in engineering, we like to look at time series also in the frequency space. And if we do a Fourier transform, sorry for the terminology, it's basically, there's no quick way to discuss it, but suffice to say that this particular peak that protrudes above everything else is centered at a frequency of 1 day inverse, roughly representing some phenomena that occurs on a daily basis, and that's the sun rising and setting. So we're looking at the solar irradiance represented by the orange, and the responses that's driven by the driver, which include, in this case, temperature anomaly, basically cooling at 10 and 25 degrees. We see that essentially the response relatively is stronger for low frequency variation. So basically, if you have a cloudy day or sunny day over a week, then MEERs becomes more effective for even those longer term variability. So to get some really clean correlation or conversion factor between the driver and the response, we look at a narrow band of the frequency spectrum centered around 1 day inverse in frequency. When you filter the time series data by this filter, we get these quasi-sinusoidal oscillations. And if we plot these two, so the driver, the solar irradiance, and the cooling in blue in a phase space, representing those two parameters, we see these trajectories, toroidal, going down and up. And the red region represents midday. So when it's most sunny, at midday we have the most cooling, and etc. Of course, there's some phase offset in the two, but we can take the phase offset into account and then collapse the data onto more or less a line. So you see a very nice relationship, direct correlation between solar irradiance and amplitude of cooling. These are for 10 centimeters. And there's some variability between the two MEERs, which we suspect to be interplay. When you have an array, it's really different from individual device. So our next stage is to look at array of different sizes and different coverage, and how that interacts with the length scale of the soil and different frequency components of the response. Apologize for the terminology. And we can also analyze the soil depth dependence. Obviously, the impact is more dramatic at the soil-air interface. So we did measurement at 10 centimeters, but if we really use the model to extrapolate to the soil interface, it's roughly 2 to 3 times more efficient for the soil interface. So with the number we measured, we are expecting roughly 10 degrees Celsius of cooling immediately under. Okay, so with our limited data collected at one site for 1 month in July in New Hampshire right here, we can actually use other correlations to project the impact for other more urgent locations, such as the western United States that's currently experiencing deadly temperatures. So here is a plot of what we call diurnal temperature variation, basically temperature at night versus temperature at midday. And obviously where you have less clouds and more sun available, you experience more variability, and also when there's less plants to do evaporative cooling. And the cooling we achieved in New Hampshire can be correlated with the local diurnal temperature. On average, 10 degrees Celsius corresponding to roughly 20 degrees Fahrenheit in this map, which is correct given we're here. So basically, if the same system were to be transplanted in California, New Mexico, Utah, whatever, we should be expecting soil at the surface or 10 centimeter depth up to 10 to 15 degrees of cooling. And that would basically mean usable agricultural land versus completely barren landscape. So there's opportunity there to use this technology to not only safeguard agriculture that's currently stressed, but potentially actually make use of soil elsewhere to make them productive as one way to gain resilience to climate change stress. So the last few slides are purely for fun, some numbers. So can anybody guess like the conversion ratio in terms of carbon storage potential? Of course, MEER is a virtual storage between MEER and the Amazon rainforest. Yes? Number 1 to 10.
No, 5.
Okay, yeah. It's roughly correct. Yeah. It's a 3. And for forests, that's in other parts of the world that are including here that are not as carbon dense as Amazonian forests. We have 1 to 6, so you're essentially spot on. But for planted forest, that's for agricultural applications, it's much larger ratio of 1 to 10. So on a per area basis, MEER is the best thing to plant. And the effect is immediate rather than over several centuries. But that's not everything. Carbon sequestration doesn't mean that you remove the climate impact. You just move from one node to another node, which has its own heating effect because forests are darker than deserts or Arctic ice. So if we also take into account climate benefit, MEERs are on average more than an order of magnitude better than forests. And compared to Arctic ice, it's roughly 1 to 3 as well. So we're trying to inspire Friday for Striker students to learn the science through this framework, and also to make like these science. I'll let you take a picture before I flip over. And we have done a calculation. If everybody carried a half-meter squared MEER on their day of demonstration, they together offset 1 megaton of CO2. And that's 100 times more than what such industrial plants can offset. So that's just an illustration, vivid illustration of the fundamental principles that we discussed today. I was giving a talk to Westminster School, like somehow Roland has some connection with the wealthy and privileged, and we were forced to entertain rich kids. But anyways, it's good to educate them a little bit. So if they were to convert their courtyard and roofs to MEER, they can offset 1,000 kiloton. And that's on par with what this guy can do with a much larger price tag. And of course, this price tag is for like low volume, and eventually we can drop that down even more. And I think that's everything I have. And I'd like to thank Edwin H. Land, the founder of Roland Institute, my colleagues, and also everybody at MEER Reflection, and you guys, and also the Open Education Network, in which we're doing these preliminary field experiments.
Thank you, Dr. Tao. That's a lot to take on board. We do have a little time for questions. I mean, I suppose if I could start by people are thinking, it's the obvious, well, 2 obvious points in a way, is how much land surface are we talking about? Is there any calculation as to, how much of Ireland, for example, we have to cover in mirrors? And then just because my own ignorance is that we're cooling the surface temperature but not the air temperature. So maybe you could explain what is the cooling effect? Is it just on the surface, or is it throughout the atmosphere as well? So no, listen, that has been fantastic. I'd love if you're happy, if you could email me that presentation to send around to people. I definitely think there's a lot more that needs to be delved into this. If the figures stack up as you say, it just leads me to, well, why is this not more prominent in the discussion? So anyway, there's a couple of questions in there. Feel free to pick whichever one you want, and obviously over to folk if you have any questions as well. But no, that was a fantastic presentation. Thank you.
Yeah, thank you. So land area, really the amount depends on your climate goal. Let's say the goal is to return to 1750 pre-industrial. Then we need about 2% of Earth's surface. If the goal is to maintain current 2020 climate, then we need to implement established MEERs onto roughly 20% of cropland by the end of the century in a more piecewise fashion. So second question about cooling of air versus land. So traditionally, when we're just, the default, light strikes land, converts into heat. That heat can travel slowly up the atmosphere and eventually radiate out. So there are several ways. One is that they go up with the water vapor. The other is direct IR irradiation from the ground. So the water vapor component, obviously, when it condenses, it will release heat in the atmosphere, so that leads to atmospheric heating. When you have a MEER on the ground, all the downstream processes are bypassed. So light comes in, goes out. There's never heat generated, so there's no heat to be spoken of for heating the atmosphere. And the cooling powers we calculated on average 100 watt per meter squared. That's how much actually makes out directly into space without secondary interactions with atmospheric particles. The actual amount that's actually reflected is 30% larger. That's basically what's striking at ground level. So that 20 or 30%, they are scattered and absorbed in the atmosphere. So they are converted into heat in the atmosphere. But we essentially speed up the speed at which that portion of energy gets out because we send them up higher rather than them having to be absorbed and then slowly make it our way up. So we also make the escape for the portion that we don't directly eject, escape faster. So these are conservative estimates. So the number I give you are conservative because we like to err on the side of caution.
Any you got a question or comment? Yes.
Basically, how would it be actually implemented to cover area? Like, would it be just mass, like wind farms, mass areas covered in MEERs, or would it be like on top of buildings in cities that you could?
Yeah, so for buildings, there's many for-profit companies working on similar schemes, including white paint, right? And also there's a company called SkyCool that uses a bit more fancy reflectors to not only do what the humble glass mirror does, but also radiate some IR through some transparency window in the atmosphere in the IR range. The problem for addressing climate change is scalability. We don't have enough roof or road or built infrastructure to really have the area to achieve the global impact. That's why we need to couple it with something in the human system that's already highly engineered, which is, in our belief, agriculture. And so that's where we have a sufficient area to do this. And if we can simultaneously bring out about co-benefits, then that's obviously a plus. And we think in the end, with fossil fuel peaking, there's no way to sustain this level of productivity for more than a couple decades. After that, what do we do, right? So we need to make use of this time to really build up this infrastructure that can be handled by individual farmers in permaculture communities while still preserving the global benefit. So it's a critical time. It's a time for making decisions. So from our analysis, it's either embarking on something as efficient as this one or better, or we'll lose the window of opportunity to do something because we would have also lost the little thermal energy we have access to through fossil fuels. The problem is so big out there that we need to work with everything we have, including the CO2 and fossil fuels. So it's not smart to to treat these issues as polarizing issues. Everything must be on the table because there's so many constraints.
Yes.
Apologies if you answered this. How localised are the effects? So if you covered the UK mirrors, that would have a direct impact on the UK. Would you be able to have is there a measurable impact in Spain?
Yes, that's a very good question. So exactly that issue is what we believe a MEER to be vastly superior from a social perspective, because it brings about strongest benefit locally. However, the 100 watt per meter squared of cooling averages, to extends to a global scale once it's scaled globally. So it's possible that local communities can build little oases, even when the global average goes to hell, and that places. And when it's only small scale, it cannot, by definition, have a global impact. So the global impact only starts to ramp up when the total heat ejected starts to be comparable to the climate monster power. So this is a scheme where we really allow decision to be local by the design of the process. So there's no discussion for like aerosol injection to be made because
That'd be the Brexit solution. Just cool Britain because we've never. But could I ask? Because again, I'm still processing this. I'm overwhelmed in some ways by what I can gather. I'm sure it's more complex. It seems to me this is economically perfectly viable, a lot cheaper than £4 million for a not even very good carbon capture and sequestration demonstration project in Switzerland.
Yeah.
The risks don't seem to be that great, and so therefore, why is this not on the agenda more? Is it a political issue? Is it that it's a fear? Oh no, we don't have to deal with fossil fuel. We can still burn fossil fuel, and this allows us to do. I'm just trying to struggle from the economic, political point of view. Why is this not more prominent in the?
It's probably because it's not profitable.
Not profitable.
Yeah, solutions needs to be solutions that people have to subscribe to and pay a monthly fee. So this one, once you have purchased your own personal set of mirrors for your crop, your garden, you're done.
Just rent people the mirrors.
Sorry, rent?
Everybody gets renting their mirrors.
Yes.
Income comes in.
Yeah.
That's happening in Germany, where German solar companies will rent your roof, south-facing roofs. So, I mean, as a socialist, I'm all for this. I mean, this is a non-profit way of dealing with the crisis. I mean, and again, I'm very excited by what I've heard. Anyway, you can all hear and see my excitement, but I'm sure you have other questions or comments. You want to?
No, only that. I mean, obviously, I wouldn't want everybody to have to pay lots towards it, but if it's the money that's holding them back from saving it, I'm sure it can be creative about that in some way.
So current flood damage is already more than what's needed to do this, to basically solve climate change from a fundamental energy balance perspective. So the damage now is already.
The analysis needs to be done on who's making profits out of what. Where the barriers are. Are there people not willing to invest because they're making short-term gains in these other?
Correct. Yes. Of course. Yeah, they're charging 500 to 600 per ton of CO2. We're saying it's like $5. So.
Yeah, you can see why the renewable energy button is attractive. In fact, it's fossil fuel plus. That's what renewable energy really is. It's not displacing fossil fuels, but there's money to be made in it.
The direct air capture plant in Iceland captured 3 seconds of emissions, yearly emissions, and the amount of investment that's gone into that plant has been huge. So it's just not feasible.
So I was intrigued by this low-cost, public good, approach to dealing with the climate crisis. Did you have to wait for the Jeremy Corbyn government at scale to institute a kind of a social democratic Green New Deal, which is like, is this debate in like in the States, just speaking of the Green New Deal in terms of,
No, they're not aware of it.
right, because it would be in that kind of space, that kind of social democratic, you know, doing public good. And so like, that's what you think is the major blockage. There's no money to be made at saving the planet,
Correct.
effectively, which I have to sadly agree with.
It's also concluded from, you know, speaking to potential investors.
Thinking of where's the money?
Where's the money? Whether it's financialization or monetization.
Maybe we should ask our grandkids rather than them,
Yeah.
in terms of a habitable planet.
Yeah.
Any other comments or questions? Yes.
Has there been any talk of collaborations with like installation artists and galleries and things? So I imagine they would be jumping on this.
Galleries?
Yeah, art.
Art galleries.
Well, landscape, intervention
Yeah.
art and that kind of thing.
We do believe that's one avenue, and there's some people artistically inclined in the group who are trying to do something similar. But we have not been approached by actual groups and people with funding to do something visible and substantive. If you are aware of such sources, please,
I was a PhD, so.
Well, I could think of one here for Queens. I mean, outside this building, this beautiful Lanyon building, during the Second World War, that was all growing runner beans and food during the war effort. It was a Dig for Britain campaign. And I could imagine, well, why not mirror? Mirrors, you know, I can even see, you know, we're asking farmers, for example, to plant mirrors as opposed to maybe suboptimal crops and so on. But again, it's that issue of how do you crack the political, economic issue in terms of making it attractive. Because I mean, again, I don't know the science behind it. I'm perfectly happy to accept what you've said as peer review and so on. But back to that issue, that it's not profitable in the conventional sense, even though it's going to save human civilization as we know it, perhaps.
No, you will not save this civilization. This civilization cannot be saved by definition
Yeah.
of the fact that it's running on the non-renewable resources. It's a way to potentially survive the collapse of the incoming collapse of the civilization, which is inevitable, right, by any measure.
But unless anyone has any other questions, we're going to thank our guest for absolutely fascinating. I don't know what I was expecting today, but that was very, very powerful.